Hi everyone! This is meant to be a video lesson introduction to our next section, 15.3, which is double integrals over general regions, as you can see up here for the header. Now, as a comment before we really get started, if you want a copy of these skeleton notes, basically a PDF of what I'm scribbling on right now, there should be a copy of those available on Moodle for you guys to fill in the blanks and follow along with. If you're not interested in doing that, if you just want a copy of the finished PDF from when I'm done with this lecture lesson, this is also available on Moodle. And finally, another comment before we get started, this is usually a 2-day lecture for me. I've tried to break it up into 3 smaller videos. Make sure that you check out all 3 of them before you try to tackle the homework or quiz. Now, with that out of the way, let's go ahead and get started. Recall from the last time that we saw each other, we discussed double integrals of functions of 2 variables over rectangular regions. Now, a comment, this is one way that I can express the rectangular region, this interval, cross interval notation. Another way that we could go ahead and do this was set notation. So if I wanted to express this as a collection of points, x, y, where x was stuck between a and b, and y was stuck between c and d, we could also express this that way. So these are the exact same sets if you had forgotten what this interval notation was. Now, at any rate, if I wanted to go and take a double integral over a rectangular region like that, there are a couple ways that we could fill this out. We could either treat this as a dy dx integral, okay, so maybe something like this, or I could treat this guy as a dx dy integral, maybe treat it something like this. The catch was that I needed to make sure that I filled out my bounds appropriately. We have to match basically my inner differential with my inner bounds, okay, regardless of which method that I use, and my outer differential with my outer bounds, regardless of which method that I use. So here for this first case, if y is my inside variable, that means that my inside bounds will be c and d, so that my outer bounds are going to be a and b, okay, whenever I go to integrate f of x, y. The exact opposite is the case for this second integral here. If I wanted to match my x values to my x bounds and my y values to my y bounds, we're basically flipping these guys totally backwards. And basically, this doesn't technically apply in all cases, but all the cases that we would run into in this class, continuous functions, bounded functions, stuff that's only discontinuous on smooth curves, basically the fact that both of these were equivalent on rectangular regions, this was a result that we got due to Fubini's theorem. Okay, so basically for all intents and purposes, in this class, if you're on a rectangular region doing a double integral, you can switch your bounds and it doesn't really matter too much. Now, with that said, what does that look like? What do I mean by a rectangular region that we've got these bounds on? This is sort of the image of what we've been doing above, right? When I specify a rectangular region R, well, here are my bounds on X. You can notice on the X-axis, my X values all seem to be stuck between A and B. On my Y-axis, my Y values for this region all seem to be stuck between C and D. When I make that restriction, in the xy plane, I get a rectangle, and on that rectangle, those are all of our input values that we're allowing ourselves to plug into this function, f of xy. Okay, and again, the way that we interpret f of xy, when you go to graph it, you're plugging in some sort of lateral point, and this is spitting out a height, and we graph all those points, we get our surface back. Okay, so remember, when we take that double integral, this is basically what we're integrating, and if you can kind of imagine this as being some sort of 3D solid between the surface and this rectangle, that's kind of what we're finding sine volume of whenever we compute that double integral. Now, the big question that I want to pose, given that our section header suggested that we were taking integrals over general regions, is, well, this. What if your R is not some sort of rectangular region like this, right? What if we don't have a rectangle? Well, there's two ways that we can approach this. Let's say that I break this up into type 1 or type 2 regions, okay? My two kinds of double integral regions. Type 1 has my region. Now note, when I say R here, I don't necessarily mean R is a rectangle again. R is just a region. For type 1, we've got a region that lies between two continuous functions of x. Now, this isn't what it's going to look like in all cases, but what I mean by this is if you want to picture your domain as just being in the xy plane, I could have one function of x here, another function of x over here, and let's say that I want to block off my region R as being in between, okay, those two curves, right? So I could maybe have some sort of y equals g1 of x, some sort of y equals g2 of x curve here, and what I'm assuming is, you know, here is my region of integration. You will notice that this is not a rectangle anymore, even though maybe it is flat on two sides, okay? And both of these guys are functions of x. You know, g1 and g2, both of these would pass the vertical line test any time that you draw a vertical line against this function. You know, it only intersects at one point. Same thing happens down here. So I've got two continuous functions of x that bound a non-rectangular region. Now, this isn't to say that we would expect to always have flat sides on our region. You know, we could get a slightly different scenario. Let's say maybe I have something like this guy. Here, again, I've got this y equals g1 function and this y equals g2 function. If I need to specify x values for my region, you know, I can still specify an A and a B down here. And again, I have some sort of general region that is no longer a rectangle. Okay, so I can't just use an A and a B and a C and a D to describe my bounds. Both of these, okay, since I've got these functions of x, these curves, serving as boundaries for my region, these both count as type 1. Now the alternate case that we're going to look at, I'll scroll down here really quickly, is let's say that we've got a region that lies between two continuous functions of y. Now the way that this is going to change things up is this. When you're talking functions of y, these are no longer things that we necessarily expect to pass the vertical line test. These are things that we would expect to pass the horizontal line test. So something like this, okay, let's say I've got a, oops, wrong thing here. Let's say that I've got x equals a function of y, so I'll call this h1 of y. Let me get my order straight. And I'll make this x equals h2 of y. Okay, both of these curves are represented by something where I plug in a y value and then it spits out an x value. So both of these would pass the horizontal line test. Okay, if I wanted to specify some sort of a interval to restrict down to so that I could get an actual region R back here, basically I've got another region which is not a rectangle. Okay, so notice before, in my previous case, I'm going to scroll up really quickly here. Notice that for these type 1 regions, we are ending up with situations where we have sort of top and bottom curves. Okay, here's another top and bottom curve for my region. In this type 2 case, I'm ending up with a situation where I have a right and a left curve. Okay, those are going to define my region. You can specify an interval, okay, to tell you how far down or up you can go, or in some cases there is, you know, kind of like above, a natural delineation. Maybe you might have some sort of a right and left function okay, which intersect in this manner so that, you know, your C and your D come out kind of naturally here, okay? So if I wanted to here, again, I've got another x equals h1 of y, and x equals h2 of y. Okay, so those would specify this region. Now, if we've got one of these regions, it's not a rectangle, the setup for our integral doesn't necessarily change too much. We've still got to specify what our bounds are. The catch is just this. If I'm worried about setting up one of these general regions, again, we just described two cases. There are two cases that I can worry about. If we've got an f that we're trying to integrate on a type 1 region, remember this was my case where I had top and bottom functions and left and right bounds on x. Well, the situation that I would want to use if I was setting up one of those integrals was to set up my integral in this manner. Okay, so you'll notice that what I'm doing is I'm making sure that my numerical bounds end up on the outside of this region. Okay, so my numerical bounds were on x. That means that this is going to have to shove dx as an outer variable for me in this integral. And when we decided that my numerical bounds go on the outside with x, that's going to force these function bounds to go on the inside with y. Okay, and sort of what you would expect with the conventional way to set up with bounds, we expect that the smaller thing, so in this case either the a or the g1, the smaller thing goes on the bottom, okay, and the larger thing, here either the b or the g2, it goes up top. Okay, now the reasoning behind this is as follows. If you'll remember, we've tried to connect the idea of these double integrals to computing volume, signed volume between this function and the xy plane. Now if you're expecting a signed volume back, you want to get a number. If I want to get a number, that means that I probably don't want function bounds out here, because when I go to plug stuff in, I'm going to get a bunch of variables back, and that's going to give me a garbage signed volume. Okay, so make sure your numerical bounds go on the outside, and those function bounds go on the inside. And this is going to be, if I scroll down just a little bit to give myself some room, pretty much the same idea for this other case. If I wanted to set this guy up and make sure that I got a number back, here, my numerical bounds were c and d, and my function bounds were h1 of y and h2 of y. Okay. For me to put the numbers on the outside and the functions on the inside, I have to switch my order of integration. So instead of being a dy dx integral like above, here you'd have to be a dx dy integral. Okay, so this is the order that we're shooting for with setting these guys up. Now again, just to make sure that we nail in this point, my numerical bounds have to go on the outside. At least they can go on the outside right now. And my function bounds have to go on the inside. Okay, so please, 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 do not try to set up one of these things with your functions on the outside. You're not going to get anything that makes any sort of sense back. Okay? Now, as far as setup, right now that's the only thing that's really changing for us. Evaluation actually looks pretty standard. Nothing really changes there. Okay, so let's see an example to make sure that we got this straight. I'm going to have you guys evaluate double integral of 2x with respect to area. And the region that we integrate over is going to be the region that's stuck between these two curves, y1 and y2. And again, for us to set up those bounds, we have to sort out what the hell this region looks like. And once you kind of finalize that, you'll notice we have y as functions of x. This is looking like it's a type 1 region. That basically means I need to figure out what's my top and bottom curve, okay? And you notice I didn't give you any numerical bounds here. This is probably like one of those area questions back in Calculus 2 where we have to either solve or graph this. and figure out where those are on our own. Okay? So, sort out all that. This is going to evaluate just like what we did in the last section. Okay? So, let's go. If I wanted to figure out what's going on with my region, one of the things that I can go ahead and do is try to graph this, right? So, if you have a graphing calculator, you're welcome to go ahead and use it. If not, we could kind of make the observation this does look like x plus 1 quantity squared. That basically looks like the square function, but it's got a shift on it because of that plus 1. So very roughly, if I'm going to sketch this thing, it looks like the y equals x squared parabola, but we've got to shift backwards, right? So we're shifting to the side by 1 unit, okay? And then, aside from that, this line should cut across this thing somewhere. Well, if I wanted to draw this, how do I know where to put this line with respect to, where any of these other points are? How do I find that? Well, let's go ahead and see if we can solve, right? So, first off, what I'll go ahead and do is I'm going to set y1 equal to y2. That way, I can go ahead and find my points of intersection. Right, that'll give me a feel for where to graph in this line if I don't have a calculator on hand. Okay, so I'm going to go ahead and do that. X squared plus 2x plus 1. This has got to be the same thing as x plus 1. Well, right off the bat, I've got some cancellations that I can take. Aside from that, I can go ahead and move the x over to the left-hand side. I will get x squared plus x equals 0. If you go to factor this out, you're getting x times x plus 1 is 0. This is going to result in the fact that either x equals 0 or minus 1. So what you're really going to get here is if you plug in 0, so there should be an intersection point here. If you plug in minus 1, which is where that apex of this parabola is, you should get the other intersection point. So this is maybe kind of poorly zoomed in here. This little shaded region, this guy is my R, okay? Goes from minus 1 to 0. You'll notice that we have the line on the top and we've got the parabola on the bottom. Okay, so I could go ahead and go off of this graph to make that note. Okay, the graph is suggesting my y1, which was my parabola. That means that since it's on the bottom, it's going to be my lower bound. And my y2 is going to be on top. So that means that this is going to be my upper bound. Now, if you weren't 100% certain, you could go ahead and check, maybe pick a test value in the middle of this interval. So something between minus 1 and 0, maybe we could pick something like minus 0.5. If you take a test value from your interval and plug it in to both of these functions, okay, both my y1 and my y2 as given here, well, if you plug that test value in, one of the functions is going to evaluate to a larger number and one of them is going to evaluate to a smaller number. Okay, remember that was our technique for trying to verify which one was the larger and smaller function back in Calculus 2. Okay, still works here, okay, if you don't have the ability to graph things. Now with that said, we have a feel for which functions are larger and smaller and which of our numerical bounds on x are going to be larger and smaller. We can go ahead and set up this integral, okay, of 2x. So I'm going to go ahead and do that here, okay. Again, numerical bounds go on the outside. We have minus 1 to 0. My function bounds go on the inside. Okay, we decided that the parabola was going to be on the bottom, okay, y1. So this means that x squared plus 2x plus 1 is going on the bottom, and x plus 1 is going on the top. And then the original function that I was asking you guys to integrate was just 2x. Okay? Now again, remember which order we're doing this in. We have said that 0 and minus 1, these are our bounds on x. This was a type 1 region with a top and bottom curve. Since these are numerical bounds on x, that means that x has to be on the outside, so y has to be on the inside. Okay? So this is how I'm going to be setting this thing up. Now, as far as evaluation goes, I'm going to scroll down here. We don't really need any of the other information. What I want to do is just treat this integral exactly like any other integral that we've done, okay, in the previous section. Previous section, we antiderive, we plug in the bounds, and then we do another antiderivative. Totally the same thing, okay? So notice when we work on these, we work from the inside out, so that means that pretty much absolutely nothing on the outside is doing anything right now. But I do have to take an antiderivative of 2x with respect to y. Notice that this acts like a constant. I should get 2x times y. This is going to be evaluated between my bounds of y equals x squared plus 2x plus 1 and my upper bound of y equals x plus 1. Okay? This is a good reason for why we wanted to use this notation, which reminds us what we're plugging in where, right? So again, per usual, whenever you evaluate bounds, you want to make sure that you plug in the top thing first. So I'll get 2 times x plus 1. And then I want to subtract off what happens when I plug in the bottom thing. So I've got 2 times x times this quadratic polynomial here. Okay, all of that is inside of this integral. Now, obviously, you don't want to integrate it like this. We probably do want to clean it up a little bit first. So I'll get a 2x squared plus 2x over here. I'm going to distribute this minus 2x through, so I'll get minus 2x cubed minus 4x squared, and then minus 2x. And I will try to also make note of any sort of cancellations that we do see along the way, okay, like the fact that I can combine some like terms here, and also just straight up get rid of others, right? So rather than trying to treat this as like a 5-term integral, it's probably going to be easiest if I clean this up and combine things like these 2 squared terms. Okay, I've got a minus 2x cubed. And after simplifying here, I've also got a minus 2x squared. Okay, and at this point, this is a standard calculus 1 kind of problem, right? We antiderive with power rule. I'm going to get minus 2x to the 4th over 4. That'll simplify to x to the 4th over 2. And over here, I'm going to get a minus 2x cubed over 3, evaluated between minus 1 and 0. Same deal as before, plug in the top number, and then subtract off what happens when you plug in the bottom number. Here this will be a minus 1/2. If we are careful with our signs, you'll note that the even power here means that the numerator here is positive, but it's got a negative sign out front. And over here, the fact that I've got an odd power means that this term will be negative, but it's got a negative sign out front, so that one will actually cancel. Okay, so I'll get a plus 2/3 here. This is going to clean up to basically these guys will cancel, and then this guy here is going to turn into a negative. If I try to find a common denominator, I'll get 3 over 6 minus 4 over 6. I'm going to get minus 1/6 back. Okay? So sign volume associated with this integral gives me minus 1/6. Now, a comment for setting this up, okay, because we've mostly seen that the evaluation is the same. Closing comment that I'll make right now, if you're trying to set up the bounds, hopefully you saw this, but it should be very reminiscent of finding areas of regions in Calculus 1, right? So if I've got a type 1 region, kind of like the problem that we just set up, let's say that you're trying to set up a type 1 region and the area looks like this, right? You know, your integral from a to b, top function minus your bottom function, integrate with respect to x. You know, this is a pretty standard area between the two curves g1 and g2, if g2 is bigger on this interval. If you've got a region that you could compute the area in this manner, then the consequence that you're going to get is, if you are doing a double integral, specifically on this region, well, the way that you would want to set up the bounds is you still want the numerical bounds on the outside, and you want your smaller function on the bottom and your larger function up top. Okay, so that's what you would be setting up. Here, since this is type 1, since this guy's type 1, we would be integrating with respect to y first and x second. If it was type 2, we'd be doing this the other way around. But again, the point that I want to make is this. We still have to have a feel for which function is larger and which function is smaller. It's just that when we're setting up our integrals, they have to go into a different spot. In case you were wondering, cheap way to figure out the area of some sort of region R, if you just integrate 1 as your function here instead of a general f, you integrate 1, you plug in the bounds, it's going to give you this exact integral right here all over again. Okay, so there's a reason that these look so close. Okay, if you integrate 1, you're basically going to get this other case back. Okay, so we're using the same exact skills to figure out which one goes in which slot for this inner bound.